Alright, so let's try this problem. We're going to try to construct the influence line for the shear at C. And there's C. You can see it's 3 feet from A. So ultimately I'm going to have to cut the structure here at C and look at the internal forces and find the shear at C. So thinking about that, let's go ahead and do a little strategy. So I'm going to want to cut the structure here at C. Which side do you want to look at? The left side or the right side? Is there really any difference? No, but just because we always usually measure X from left to right, I'll look at the left side. Okay? Now if I've already made that decision and I cut my free body diagram, that means I need to know the reaction at A. So I'm going to have to first figure out the influence line for the reaction at A. So let me go ahead and make an assumption for the direction of AY and BY. I'll come over here and draw this it'll be a little bit easier to see. So let's draw it again. So there's my unit load for my influence line at some distance X, and I'm looking at AY and BY, and I'm trying to find AY. So how can I find AY? Some moments about B, right? And if I do that, what's this distance? If the distance from the left edge to the unit load is X, 12 minus X. So now if I sum moments about B and make sure I'm in equilibrium, what do we have? Well, the unit load creates positive moment, so that's 1 times a moment arm of 12 minus X. And then AY creates negative moment about B with the moment arm, the total distance is 12. So what's AY equal to? It looks like it's 1 minus X over 12. Okay? Even though that's not the part that we need, I'm going to go ahead and plot that just so you can see it. So there's AY as a function of X. So when I put in X equals 0, I get 1. I put in X equal 12, I get 0. And it's linear. So that's what my influence line for AY looks like. Any questions about that one? So where would I stand if I were a unit load, a moving load, to create the maximum reaction at A? I would stand at A. And if I want to create the least influence, where would I go? I'd go over here and stand at B. So now with that said, let's come up here and draw the free body diagram for this section. Remember, I'm looking for the internal shear at C. So there it is. Positive shear is down. And what's my reaction at AY? 1 minus X over 12. You guys see that? And then my unit load will be here. And for that case, that would be where the unit load is located on the first 3 feet of the beam. Now, since I'm going to find the shear, I'm just going to sum forces, so I don't really care about its position. So when I sum forces in the y direction, I'll assume up is positive. What do I get? Well, my shear is acting down. 1 is acting down. And this is acting up. So that would be plus 1 minus X over 12. So solve for the shear at C, and what do you get? Negative x over 12. But that's only valid for the first 3 feet. Because what happens to my free body diagram when the load goes between 3 and 12? Well, my reaction is still the same because it's a function of that position, 1 minus x over 12. So it's behaving as the load moves as a function of x. This is still my positive shear at C. Where's the unit load? Is it on this section? No. So I do the same thing. I sum forces in the y direction, set equal to 0 for equilibrium, and now what do I have? Well, I have my shear at C acting down, plus 1 minus x over 12. So my shear at C is equal to 1 minus x over 12. So all I need to do is plot those two. So I'm now plotting the shear at C as a function of x. So there's 12 and there's 3. So from 0 to 3, I plot this equation. So when I plug in x equals 0, what's the shear at C? 0. When I plug in 3, what's the shear at C? Negative 1/4, right?
Did you mean for this second equation 3 is less than x less than 12? Did you mean to write the length of the is 3 feet?
It is.
It is.
We're cutting it at C, so that segment of the structure is 3 feet.
The 0 is less than x is less
This is the position of the unit load.
Oh. Okay.
So the unit load is between 0 and 3, so it's on this body. This is the position of the unit load is now 3 to 12. It's not on that free body.
Yeah.
So let's plot this. So what is this when x is equal to 3? It's 3/4, right? And when x is equal to 12, it's 0. So this is what the shear at C looks like. Now I want to show you one thing. This total change right here is equal to what? 1. So the change in shear as you go from the left side of C to the right side of C is equal to 1, which is exactly equal to the value of the unit load. So that says that as I approach C from the left side, when I'm just to the left of C, I'm creating negative 1/4 of my weight in shear. And just as I step past C, I jump up to positive 3/4 of my weight. There's an instantaneous change in shear. If you're designing a connection at C, which of these two values is the most important? The maximum, right. So it'd be 3/4. The sign is not important. It's the magnitude. Also, if you look carefully, the slope of these two lines is exactly the same. X over 12. X over 12. So it just shifts as it goes over. What do you think of that? So any other questions about that one? We'll work several more.
So you just to get the negative 1.3 you plug in the 3 feet into the shear equation, right?
Right. So this equation right here is minus x over 12, and then this equation here is 1 minus x over 12. So this equation is good from 0 to 3.
Right.
And this one's good for the next 9 feet, which is
The second one.
3 to 12. Because remember, this distance over here is 12. I know it's a little different than you're used to seeing, but if you just keep the basics, just think about the fundamentals, then the curve will kind of develop itself. You can see the equilibrium that we're doing. The statics is not that difficult. It's the setting up of the free body and the concept of turning this into the problem. The actual execution, I think, is not that challenging yet. Okay.